All right. Well, thank you very much, Abby. Appreciate being here. And first of all, I'd like to thank the support for AGI in putting this together, but also for the support in putting together these mapping products for the state of Michigan. And that's Mr. John Esch, who's a contract geologist with us, and Dr. Alan Key, who's been a glacial geologist for almost 30 years here in Michigan. And I've put some links on here so other people can get some of the files that we're going to be talking about. But the Great Lakes Geologic Mapping Coalition has been the supporting body that has helped to develop Illinois plus the other Great Lakes states, and Michigan has been woefully behind in doing a lot of mapping because there just wasn't funding to go with it. But all the targets that we used over the last 25 years are the same: geological, environmental, societal, and economic benefits. The Cass County project was brought about because of a need, and the need is because it was a geologic dead zone. It had high agricultural demands. The area down in the southwest part of the state is one of the highest agricultural growth areas and monetary areas in Michigan, but also in the region, perhaps selectively in certain years in the United States. There's scientific demands that were met, better understanding, unraveling the glacial sequence, and also the aggregate resources, all those things that have been talked about by other people. One of the things that's important, if you saw it on all the other slides, is that the Lower Peninsula of Michigan, remember we have two peninsulas in Michigan, the Lower Peninsula, about 60% of the water comes from glacial material. And so the state does permit high-capacity wells. That's for irrigation wells, and that's the map on the left. The red square shows where the mapping area that we're doing, and if you look at the map on the right, that shows where we have put together sufficient detailed subsurface and superficial geology to have a better understanding of the geologic framework. Most of the state hasn't been mapped. We've only mapped 10%. The dead zone is down here in Jones and Vandalia. This is the techniques that we use. They're similar to all the other surveys, but the two things I want to leave you with is that the passive seismic has been a real tool for us because we just don't have a lot of money to spend on a lot of drill holes. It enables us to identify the bedrock contact, and also lidar. Having new lidar information, and again, Michigan has been behind the other states. We're just now starting to get lidar so that we can use it because it helps us become more efficient, and that means that we get a higher return on our dollar and our mapping products. This map just depicts where the mapping area is, the red box, and we have essentially two, if not three, glacial lobes that occurred during the same time frame. That's from the lower one down below Erie is less, but we have the Huron, and for sure the Saginaw and the Michigan lobes. These are the three that interacted in our mapping area. This is a DEM, digital elevation model, for our area, and this, of course, is based on 10-foot contour intervals. We show the Lake Michigan lobe, we show the Saginaw lobe, and we show some of the other features that are there. And then, of course, we have the two quads that we've just completed mapping. Those are two 7.5-minute quads. These are the completed quads that we've done, and we've tried to put together a package so that we have sufficient detail that people can go away with. We have the map with the geology, plus we show where the drill holes are in the center, and down at the bottom is where we've been using the Tremino on our maps for the last 5 or 6 years. This shows the bedrock contour as well as the thickness of the glacial material, and then we have DEM maps and other things. The bottom doesn't show up very clear here, but I'll show you that's the cross-section through the area. We put one cross-section. This one goes from the northwest corner of this quad down to the southeast. This is the Jones, immediately adjacent to the east. This shows the geology that we have, and again, to repeat, we got the drill hole logs, the information on that, the bedrock topography with the Tremino, as well as the cross-sections. This is the technical report that we prepared, and this puts everything that I'll be talking about in more detail. It's available on our website that's on the site. What were the milestones that we achieved in this mapping program? This was the first mapping program where we had actually received money from the state of Michigan. Prior to that, it was just funds that were available from staff working on mapping projects. But we were able to identify that we had a glacial drift in that particular area that was 200 feet greater than any of the published data has been there. We also identified through the mapping that we had an irregular bedrock surface that was valleys and ridges. And it was the first evidence from a geologic perspective of the Saginaw and Lake Michigan lobes were intermingling active together at the same time in geologic time. And this is relatively significant because it overprints each other in the mapping that we did. We had a collaborative drilling program. The Illinois State Geological Survey wireline rig was contracted to come in because we could get quality work done by people who understood exactly what we wanted to do. This is an example of one of our logs. The left is the litholog that we do in the field with the core that you see on the right. We gamma log each hole so that we can tie the lithologies to that. And then we take all of our core and then we sieve analysis it, and that's what's on the right. This to give us a grain size analysis so that we can then start depicting what the conductivity values are and can be for these particular cores. The blank areas are areas where we didn't get recovery, and this is because it's primarily sand material that's in it, and we couldn't catch it in the core. Of note, down at the bottom, the passive seismic, in this case, predicted that we had about 460 feet to the bottom of it, and it was 456 feet where we tagged the bedrock. We also look at bedrock valleys, because bedrock valleys geologically in Michigan as well as in the other areas are a potential resource for water. And if we look at the map that we're depicting here along Lake Michigan, the bedrock valleys are oriented northwest, southeast, and that our area where we have our mapping in red doesn't appear to have much because there's not a lot of data down there either to show it. So using the HVSR, again, just for a moment, is what was the gain that we got out of it? We were able to estimate the thickness of 300 to 450 feet. We didn't have water wells. We could go ahead and do calibration when we tagged bedrock. We didn't have the expense of drilling a number of holes, but drilling selective holes so we could get good stratigraphy. And then we didn't run geophysical surveys because that's another technique for being able to map the bedrock. So we have a much higher return on investment by using the HVSR passive seismic and being able to identify where the bedrock lows are and where we can get the best bang for the buck in drilling. Here's our standard DEM that everybody's using, 10-foot difference. And then here's a generalized projection of the bedrock projected into this with the 42 data points that we had over these two quads. It shows a pretty rough surface. Here's the passive seismic unit. You saw that in one of the other ones that Harvey had shown, but this is 16 to 18 minutes of reading, and it takes probably 25 minutes to a half hour, and you can have the data from a single point. Here's a mapping products that we did. What we're showing here on the left, this is the bedrock topography, and we've combined the two quadrangles I showed, Vandalia on the left, Jones on the right. The top two are the two that we're going to be publishing in another month, or this month actually. But what it shows is that we have a bedrock valley that's oriented, or two of them that are oriented nearly north-south, which is not the same as the other orientation. So it's a projection that possibly that some of the bedrock valleys are actually pre-glacial in origin, and that they may represent old channels that are on the old bedrock surface, but that's yet to be defined. Then, of course, we also predict where the thickness of the material is. We use 186 readings in this area. Here's a detailed cross-section. This is Vandalia, the one on the west, so it's northwest down to southeast. But we show where the water table is, and I've got the triangles indicated on there. The unique thing about this is that in many parts of Michigan, we have water that is at different levels. So we have confined, unconfined systems. In this particular one, where it appears as if we may have one of the greatest thicknesses of glacial material, we seem to have one water system. And so this is really unique in this particular area. And you can see where the wells are completed at the very top. That's the yellows of sand and gravel going across. And we're showing in this that the wells are completed at different levels. Water levels are all the same. The bedrock contour is down at the bottom. The arrow off to the right is the one drill hole that's common to the two cross sections that we're going to show. So we've got a single water level, which is a made of water storage. Much of the drilling and completions were in the upper 150 to 200 feet. We're down to 250 to 450 feet. Here's the Jones cross section, when it's approximately north-south through the section. Again, the water levels, again, the same. We have a single unit, and that single unit of water is shown all the way across. Then, of course, we've got the actual bedrock contour. The blue area that you see on the bottom, very irregular. And this is showing this that we have deep valleys that are also in this particular area. And this is another, if you will, derivative value that we have that we can then identify where we could look for deeper aquifers in the area. LIDAR, and we had talked about LIDAR in the other discussions. It's probably been the savior for a lot of work for geologists right now in the Great Lakes area and other parts of the country. But it helps us to focus our field efforts so that we're not going around looking for things. It helps us to direct us to go look at them. The arrow in there shows a feature that will show up, and I'm going to show you right now. That's that big arrow in this topographic map. It's an esker, and it shows up. But if you have features that are less than 10 foot on a standard topographic map of 10-foot contour intervals, they don't show up. And where we got the question marks there, that's hummocky topography. Yes, it has elevation difference, but what does it really mean? So we look at the LIDAR, and again, the esker shows up on the bottom. What are these features? They're linear, about a half-mile wide, almost a mile long. What are they? And as we went out and looked at them, Looking at it in the hill shade on the top right, it turns out what we have is we have the Lake Michigan lobe now compressing the glacial sediments from the Saginaw lobe and thrust faults. And these are small micro thrust faults that are in the area trending north, east-northeast across the area. And that's an example of a recent study where the thrust faults are in an active glacier area. But this type of lidar had us go out there and look at it so that we could actually see it, so that we could look at the different stratigraphy in there and see that it was thrust faults. These features were not on the topographic map. Just another couple quick looking at topo maps. What do you see on a topo map? That arrow just doesn't show much. This happens to be one of the highest elevation areas in southwest Michigan. Looking at this under the lidar, we see that there's a feature off here off the high elevations. And what is that feature? As we blow it up, lo and behold, we find out in the trees over here there was an old excavation. This was an old gravel operation that had been in place. And so it can help to identify recent activities, dumps and other things that were on site that you just don't have any evidence on topographic maps. It says go take a look at it. And you can see the picture on the bottom. This is actually the remnants where the coarse gravels were actually carbonate cemented, and they were left there because the gravel operation was just looking at the loose material. So what did we really gain out of this mapping program, out of this dead zone? Our maps go back to 1915, over 100 years, and that's the basic maps that we have for Michigan. And what we have done in working with the Great Lakes Geologic Mapping Collaborative is we've learned from each other, and by having the working sessions, the annual and sometimes biannual sessions that we've had, we know that by putting it into ArcGIS and putting it to formats that we have people, not just the geologists, but other people can use the data. In this particular session that we have in Cass County, we have another success. We have a hydrostratigraphic assessment of a little-known complex geologic setting. And so we have stratigraphy and water levels. There's a single hydrogeologic zone. This was not known before, but now we know it. LIDAR identifies features so we could go out and quickly identify them, confirm that they weren't shown on the maps, and we were able to start unraveling a complex interlobate area in the east central part of the county. It wouldn't be there if we didn't have a LIDAR. We wouldn't have gone to look at it probably. The drift thickness is about 100 to 250 feet greater than the published reports, and that's from the water well data. So this helps us to go out there so we don't have to drill all of the holes, but we could selectively drill by using that. And what's the geologic mapping documents? What are the returns that we get? We have water and aggregate resources, we have detailed stratigraphy, and combined we have the highest return on investment in this 2.5-year mapping period, and that's what Dick had talked about in the original program. What I'm showing you in the next slide is a picture composite that was put together by John Ash, where he has put together each time frame in small little segments. It's not to be an animation, but to just show you how it changes. But in this particular area, the red area is the mapping area. And this is looking at the elevation model and how he depicts the tunnel valleys, those little dotted lines that are going through there. And the yellow is the outwash as it forms. And then we have the tunnel valleys coming from the Michigan lobe. Then we have the drumlins up to the northeast on the right. And we have outwash in different areas where it's been highlighted. And then we have the final drainages. There's a lake that just shows up there, and the tunnel valleys and the outwash that shows where we get the overprinting from there. And then it just shows you where those thrust faults were located, and then the final drainage. And these are the kind of things that can be put together so that people can get an understanding, stop and take a look at it. So that's all that I have.